Hello. In this tutorial, we're going to take a look at AP Physics 1, Unit 4, Work and Energy, Student Workbook, Activity I, Gravitational Potential Energy. In this scenario, we have an astronaut lost in space near an alien planet and its orbiting moon, as shown to the right, not to scale. At a particular instant, the moon is directly opposite the astronaut and, on the far side of the planet, in line with the center of the planet, at a distance r from the astronaut. Mark an X from the diagram to indicate the location where the astronaut could move so that she would not feel a net gravitational force. Well, if we look at the picture here, since the planet is way bigger than the moon, that spot that we place the X is not going to be right in the middle, okay? Because bigger mass needs to be balanced by a longer distance. So we need to move this closer to the moon, such like that. In other words, the moon has a smaller mass, so that should be matched with a smaller distance. If the planet was not between the astronaut and the moon, but distance r was the same, would the gravitational force by the astronaut by the moon increase, decrease, or stay the same? The equation for gravitational force, if we look at it, F equals big G, mass of the moon times mass of the astronaut divided by r squared. Notice it does not contain any information about the planet. The gravitational force would stay the same. Part C. The astronaut's jetpack is powered by an arc reactor that can supply nearly limitless energy to the suit's thrusters. The astronaut wishes to escape the planet-moon system and travel to other parts of the solar system away from any other significant gravitational effects of other planets or moons. Consider the energy required to escape from the configuration as shown. If the astronaut was instead standing on the moon, would it require more, less, or the same amount of energy to escape? To escape the gravitational attraction of an object, one must be infinitely far from that object. So if we consider the energy usages, the minimum energy usages, the energy will become zero once she has escaped. We can say that we have the energy would be the energy of the jetpack. In other words, the work done by the jetpack. Work translates into the change in kinetic energy done by the jetpack, plus the gravitational potential energy of the moon planet system will equal zero. So the total energy would be the work, and this will be derived in class at a later time. But we have the negative G times the mass of the astronaut times the mass of the planet over D, the distance to the planet. That kind of represents the change in kinetic energy, the work done. Again, we'll derive that later. Plus the gravitational potential energy relating the astronaut and the moon, where r represents the distance of the moon. So if she is on the surface of the moon, the r value significantly decreases, this whole potential energy increases. Well, that means if the potential energy increases, she needs to do more work with the jetpack in order to escape. In other words, it'll be harder. Part D. The astronaut is able to travel a very far distance away, x, from the planet-moon system at a constant velocity, needing a total amount of energy to do so. Explain why the jetpack must do work on the astronaut to maintain a constant velocity. Well, this is because there is a net force acting on the astronaut, and it's always pointed back towards the planet-moon system. We're talking about gravity. Even if you get really far away, there's still a gravitational attraction pulling you. It just gets weaker and weaker. So without an opposing force going forward for the jetpack, the astronaut would experience negative acceleration and would slow down. So the jetpack allows for an opposing force to balance the net force due to gravity and allow the astronaut to move at a constant speed. Part 2. Sketch a graph of the force exerted by the jetpack versus x to keep the astronaut at a constant velocity as she moves away from the planet-moon system. Identify the features of the graph that could be used to determine the energy used by the jetpack to move the astronaut in this manner. Well, the force by the jetpack, as you get farther and farther away, you're going to experience less and less gravity, which means if you experience less and less gravity, the jetpack needs to expel less and less force to keep you going at a constant speed. Therefore, you should experience less and less and less and less and less force by the jetpack over time. Since the net force is 0, the force from the jetpack must equal the force from the planets. The force decreases with a 1 over r squared trend. The area underneath this graph represents the work done by the jetpack. Part 3, describe the power from the jetpack as the astronaut travels away from the planet-moon system. Power is the force times the average velocity. So if we consider the velocity to be constant and we see that the force decreases, the power will decrease as well.